So what powers our bodies, our cars, and even our phones? Well, it all comes down to a type of chemical reaction that's happening literally everywhere all the time, usually completely unseen. They're called redox reactions, and today we're going to pull back the curtain on the hidden chemistry behind, well, just about everything. Okay, think about this for a second. You've got a roaring campfire, right? Then you have the slow creep of rust on a piece of metal. And then there's the battery powering the device you might be watching this on. On the surface, they couldn't be more different. But what if I told you they're all connected by the exact same fundamental process? Yep, you guessed it. The answer is redox. Every single one of those things is a real-world example of this fundamental chemical dance, where electrons are passed from one thing to another. It's the invisible engine that's driving all of them. To really get a grip on redox, we kind of have to go back in time and see how our understanding of it grew. Originally, scientists saw these reactions through a much simpler lens, and it all revolved around one key element: oxygen. So, back in the day, the idea was pretty straightforward. Oxidation, that just meant you were adding oxygen to something. Think about magnesium burning. It combines with oxygen and poof, you get magnesium oxide. And reduction, well, that was just the opposite, removing oxygen. As chemistry got more advanced, the definitions got a little broader to include other elements, but that core idea of a matched pair of opposites stuck around. But here is the absolute key, and it's still true today. You can't have one without the other. They're a total package deal. Chemists quickly realized these reactions always happen in tandem, which is how we got the name we use today, redox. It's literally squishing together reduction and oxidation. But this old school idea, it had a major flaw. Sure, it explained a lot of reactions pretty well, but it completely fell apart when it came to reactions that didn't involve oxygen or hydrogen at all. Chemistry needed a bigger, more fundamental principle to explain what was really going on under the hood. And that's where the big breakthrough happened. Chemists totally shifted their focus. Instead of just looking at atoms like oxygen, they started tracking something way smaller, way more fundamental: the electron. By following the electrons, they unlocked a whole new, much more powerful way of understanding these reactions. This new electron-based view gave us a much cleaner definition. Oxidation is, simply put, the loss of electrons. That's it. It doesn't matter what element it is. If a chemical species loses an electron, we say it has been oxidized. And of course, if oxidation is losing electrons, it just makes sense that reduction has to be the opposite. Reduction is the gain of electrons. So any atom or molecule that grabs an electron is said to be reduced. They're still perfect opposites. So how on earth are you supposed to remember which is which? Well, there's a classic mnemonic that chemists have used for ages that makes it super easy. Oil rig. Oxidation is loss. Reduction is gain. It's a simple little phrase, but believe me, it works. Let's make this real. Think about making plain old table salt. What happens is a sodium atom gives away an electron, so it's been oxidized. A chlorine atom swoops in and takes that electron, so it's been reduced. Now you've got these two ions with opposite charges, and they attract each other, forming sodium chloride. We can even think of it as two little half reactions coming together to make the final product. Okay, so tracking electrons is a powerful idea, right? But let's be honest, in really complicated molecules, it can be tough to figure out who's gaining and who's losing. To deal with that, chemists came up with this really clever bookkeeping system. It's called oxidation numbers. Now, there are a few rules to this game, but the core idea is pretty simple. We basically just pretend that in any chemical bond, the atom that's more, well, electron-hungry gets all the electrons. This lets us assign a kind of hypothetical charge, our oxidation number, to every single atom. It just gives us a crystal clear way to track where those electrons are flowing. All right, let's see it in action. In this reaction, look at the copper. It starts out with an oxidation number of +1 and ends up as pure copper with an oxidation number of 0, so its number went down. Now look at the sulfur. It starts at -2 and ends up in sulfur dioxide with an oxidation number of +4. Its number went way up. And that right there brings us to our most precise and useful definitions of all. Oxidation is simply an increase in oxidation number. Reduction is a decrease in oxidation number. Using this system, we can analyze pretty much any redox reaction with total clarity. Okay, enough with the theory, right? Let's see how these reactions actually play out in the real world. Because redox isn't just about numbers on a page. It's about a fundamental competition for electrons between different elements. A classic lab experiment shows this perfectly. You take a strip of zinc metal and you place it into this bright blue solution of copper nitrate. Almost immediately, this fascinating exchange starts to happen. The zinc atoms give their electrons to the copper ions in the solution. So the zinc dissolves, it gets oxidized, while solid reddish copper starts plating onto the strip. It's getting reduced. That fading blue color is the visual proof that this electron transfer is happening right before your eyes. It just goes to show zinc is way more willing to give up its electrons than copper is. And using this whole framework, we can start to classify redox reactions into different types. For instance, that zinc and copper reaction, that's what we call a displacement reaction. But there are others, like combination, decomposition, and even this really weird one called disproportionation, where the same element gets both oxidized and reduced. The main takeaway, though, is that this core principle of electron transfer is happening across a huge variety of chemical changes. So, what's the big picture here? Why is this all so important? Well, because this constant, non-stop exchange of electrons is the engine that drives our world, from all of our technology to the very processes of life itself. You know, one source puts it perfectly, chemistry is essentially a study of redox systems. And when you really start looking for it, you realize just how true that is. At its very core, chemistry is the study of how and why electrons move between atoms. And the applications are truly everywhere. Burning fuel for energy, the batteries in all of our devices, getting pure metals from rock, the rusting of iron, all of it is redox. Even the way our bodies turn food into energy through respiration, yep, that's a slow, controlled biological redox reaction. So the next time you see a fire or use a battery or even just take a breath, you'll understand that hidden chemistry that's really at play. It's all powered by this elegant and universal dance of electrons. And now that you know the secret, the real question is, where else are you going to see this